In this video, we're going to talk about how to conduct a two-way ANOVA. So a two-way ANOVA is a multivariate method. It's an extension of a one-way ANOVA to analyze the relationship between a quantitative response variable and two categorical explanatory variables. So up until now, we've been doing one-way ANOVA, which allows for just one categorical explanatory variable. This is called multivariate because it allows for more than one explanatory variable. So the example that we're going to look at is about the eye contact effect. So there were 10 male and 10 female personnel officers, and they were shown a front view photograph of an applicant's face and were asked to rate the likely job success of the applicant on a hilarious scale of 0, which is a total failure, to 20, which is an outstanding success. Half of the officers in each gender were chosen at random to receive a version of the photograph in which the applicant made eye contact with the camera. The other half received a version in which there was no eye contact. So essentially we end up with 4 groups: female and no eye contact, female with eye contact, and male no eye contact, male with eye contact. So we have our response variable, which is the success rating, and this is quantitative. It's on a scale of 0 to 20. And then we have 2 different explanatory variables here. We have gender and eye contact, and both of those are categorical. They're actually both binary in this particular example, but that's not necessary. This would work even if the variables had more than 2 categories. So with a one-way ANOVA, we were really just using the group means as a way to predict the response variable. Here we're going to write out a model that shows how the predicted value can be thought of as related to both the gender effect and the eye contact effect. So for our predicted ratings, we're going to start off with our overall mean, which is 13.05. That's going to be our starting point. And then we want to add an effect for gender. So for finding the effect, we're going to do the group mean minus the overall mean. So this is pretty much like what we did when we were calculating SS groups in a one-way ANOVA. So like for female, it would be 15 minus 13.05, and that comes out to be 1.95. So basically we're starting with the overall mean of 13.05, and then we're going to add 1.95 if the officer is female, the person doing the rating is female. On the other hand, if we subtract 11.1 minus 13.05, we'll get negative 1.95. So if the officer is male, we're going to subtract negative 1.95 for the predicted rating. And these are obviously just positive and negative opposites of each other. This will work if you have balanced groups, like we have 10 female officers and 10 male officers, and so it comes out even on the 2 sides. Similar kind of thing we can do for eye contact. So if there was no eye contact in the photo, that was a mean of 11.4, and we're going to subtract that overall mean, 13.05, and we get a difference of negative 1.65. So this is telling us that we should subtract 1.65 if there was no eye contact, and add 1.65 if eye contact was present. So now we have a model to predict the ratings that depends on those 2 effects, the gender effect and the eye contact effect. And I think setting it up in terms of effects is helpful for our calculations. So I'm going to show you how to do all of this for gender, and then I'll leave the calculations for eye contact up to you. Okay, so let's say we want to calculate the sum of squares for gender. This is going to be based on those effects. So we're basically taking the effect squared, 1.95 squared, and remember that was the group mean minus the overall mean. So this is basically like what you did when you calculated SS groups back in one-way ANOVA. And we want to repeat this for however many female officers there were in the sample. So there were 10. Plus, we've got negative 1.95. This is the effect for male officers. We're squaring that. And there were 10 male officers. So obviously we could just add these all up. We could do 1.95 squared and multiply that by 20. But I'm writing it this way because it's a little bit more complicated when your variables are not binary, because you're not going to just get positive or negative. So sort of nice to think about it this way. And when you add all of that up, you end up with 76.05. So that's where that sum of squares came from in the table. And I'm just going to put a note here so you'll remember later that what we did was very similar to SS groups calculation. So if you wanted to go back to your previous notes for SS groups, that might sort of help for justification. For our F statistic, this is always the mean square, so in this case the mean square for gender, divided by the mean square for error. So remember, mean squares are going to be the sum of squares divided by the degrees of freedom. So the sum of squares that we calculated was 76.05. The degrees of freedom is 1, and that's because we have 2 levels for gender. Gender was being treated as a binary in this example. So we had 2 minus 1 gives us 1 degree of freedom for gender. And then for the mean square for error, I'm going to pull from this other table, the analysis of variance table. And I've got 98.45 divided by 17. And that together gives me an F statistic of 13.1320. And to show how to calculate that p-value, I could use an F distribution. We've got that distribution calculator. And I'm going to have to put in different degrees of freedom. So I've got the numerator degree of freedom was 1 because the degrees of freedom for gender. And then the denominator degrees of freedom is going to be 17. That comes from error. And in JUMP, I'm going to add-ins, teaching modules, distribution calculator. And I'm picking the F distribution. And I'm going to change my degrees of freedom to 1 and 17. Then I'm going to put my input value is my F statistic. Which is 13.1320. You can't even really see it on the picture, so this would be a pretty extreme value, a value that would be unlikely to occur if the null hypothesis were true. I'm going to pick greater than, which I always do for an F test, and I end up getting a p-value of 0.0021. My p-value is 0.0021. So remember, the null hypothesis is always going to be that there is no effect. So in this case, there's no gender effect, that the mean rating is the same regardless of gender. So if our p-value is really small, we have strong evidence against that null hypothesis. So in this case, it would be strong evidence that the mean ratings differ based on officer gender. So to make sure you understand those calculations, start with the eye contact effect that we calculated before, and use that to calculate the sums of squares, the F statistic, the p-value, and draw a conclusion. So go ahead and pause the video while you do those calculations. Okay, so I filled it in so you can check your work. And let's go ahead and fill this into the table too. So our sums of squares was 54.45. Our F statistic was 9.4022. And our p-value was 0.0070. And let me show you how these two tables that we have fit together. So if you add up the two sums of squares, you'll get 130.50. Notice that in the analysis of variance here, that's shown as the model sum of squares. And also if you add up the degrees of freedom, you'll get 2, which is the model degrees of freedom. And actually, if you look at it in our book sort of combines these two tables. So instead of including a row for model, our book includes 2 rows, one for gender and one for eye contact, and it puts it all together into one analysis of variance table, whereas JUMP splits it up into 2. But basically, you can think about SS model as being all of the variability explained. Right, so this is the variability explained by the model. And in this case, the model includes 2 different predictors. So this is the model that includes gender and eye contact. So just to summarize what we did here, we started off by writing a model in terms of two different effects, the gender effect and the eye contact effect, but all of that was based on the sample means. So those means are going to vary from one sample to the other, and it's possible that they could have occurred just by random chance, right, just because of sampling variability. So we decided to carry out an F-test. Looking at the F-test, we ended up with very small p-values for both of them. So that means if there were really no gender effect, it would be unlikely to get a sample effect of 1.95 or greater. And in the same way, if there were really no eye contact effect, it would be unlikely to get a sample effect of 1.65 or greater. So it turned out that those were large enough to provide convincing evidence of an eye contact effect and a gender effect.